Welcome to the RF lecture series. Here in this we'll discuss about the noise topic. Noise is random. That is nothing but, for example, we'll see this is the voltage which is a steady state. Here there is a no change in the amplitude, or else if there is a signal in which it has the equal amplitude, that is this is the, let us consider this the voltage V1 in which this amplitude there is an equal, and here this noise can be of random and it is extended in the various form across the frequency spectrum, although it is not always in the same amplitude. That is, this amplitude is we get the disturb. So if we have the noise, then this amplitude of the signal will get vary. And here there are different types of noise. White noise, which it affects the frequency equally, and it spreads up from the zero frequency upwards with the flat amplitude. That is, there is a no change in the amplitude. The amplitude will be the same, whereas that the frequency will be the changing. And here the pink noise, it does not have the flat response. That means as the frequency increases, that power density is getting the decreases. And here's the band limited noise, and this noise can be of in the frequency of band limited. That is, whatever the band which it affects only the noise, it will be in the band limited. So this limited band noise occur either in the filter or in the circuit when it passes. What is the effect of noise? There is a variation in amplitude caused by the noise can mask out the signal. That is, the signal will get masked out. So the data will be added with the noise, so that our data will get increased. So that we'll have the large amount of data error. So when the data error is large, then we'll have the increased amount of bit error rate. For the bus performance, the signal should be very clear. That is, we have to separate that noise with the signal. So in many instances, we will not be have in real time data, they will not be have the data without noise. Already we will be having the noise with that. So there will be the acceptable level of data errors or a signal to noise ratio. So which when the signal is reduced, when the noise is getting reduced, then the cost will also get reduced. Now let us consider this is an signal. So here, for example, we'll have the RF system where here this is the signal whichever is transferred, and our RF system is like noisy. It's noisy, so that our signal will get disturbed. Here you can see this, that our signal has been disturbed with this noisy. And the different types of noise. Here you can see this is the thermal noise. Thermal noise has occurred due to the thermal agitation of charge carriers, typically electrons in the conductor. That is, when we are getting the signal has been transferred due to the electron conduction, that level of moving, it will be causing the thermal error. And short noise. Short noise is nothing but the short fluctuation of electrical pulses. So this form of noise that rises from the time dependent fluctuation in electric current. So it originates from the discrete nature of the electric charges. Next is the phase noise. Phase noise we can call as in is a form of an RF noise. So the phase noise is a form of RF noise that is visible on radio frequency and other signals. So it appears in the form of phase jitters or the disturbance on the signal. Next is flicker noise. Flicker noise is one type of noise. That is, this flicker noise occurs in the low frequencies. So the flicker noise occur in virtually in all electronic components. The flicker noise is proportional to the inverse of frequency, and it can be shown as a variety of effect, but often occurs in the resistance fluctuation. See here you can see this image. Here we have the flicker noise, and this is a thermal and short noise is occurring in the high frequency, and here this flicker noise occur in the low frequency. And here you can see this is the breakdown point where here you can see the flicker and thermal noise short noise has been corner frequency, where this is get the flicker noise and short noise gets separated. It doesn't mean that the thermal noise and short noise is not occurring in the low frequency ranges, but whereas it occurs in the low frequency ranges is also. This thermal and short noise is common in all the devices. And next is the avalanche noise. Avalanche noise is a form of noise that occur in the PN junction that are operated in the region or close to the point of avalanche breakdown condition. And here we'll not discussing about the avalanche noise, but here I'll tell you what that whenever that avalanche breakdown condition is occur, there will be the slight disturbance, that is the noise occur, that we call as an avalanche noise. The noise is measured with the signal to noise ratio. So how we measure the noise? So noise can be measured using the SNR ratio. So SNR is signal to noise ratio. It's a measure used in engineering and science that compares to the level of the desired signal to the level of the breakdown noise. For this signal level, we should have the high SNR. That is that our noise ratio should be the low, and this SNR signal to noise ratio we'll use will measure in the form of decibel. So that we call in the decibel 10 logarithmic. We say it is of this is we can say as a SNR. So here for all the RF systems, it doesn't mean that we don't have noise. We'll have the noise, but there will be some acceptable level for that any applications. Now we'll see about the dB and dBm. dB is a decibel, the logarithmic unit used to express the ratio of two values of physical quantity. One of this value will be the standard to the reference value. So this is the one of the important measure we use in the radio frequency. Like this is the power, how we measure in terms of power can be measured in terms of dB, and here we can see this formula of 10 log of 1 by P by 1 watt. So for example, if we are giving the power as in 1 watt, it doesn't mean that if we do that logarithmic 1 by 1 will become 0, 10 log of 10 will become 0. That means for the power of 1, that your decibel level is 0. So based on how we are giving this power, our decibel power level, it will become of changing. So it will be like we have to compare between this standard and the what are the reference level is acceptable level of power references. And here you can see this between this two, we already I have said that we have to measure between these two power levels. So here you can see this power in dB of 10 log of P2 by P1. P2 is a power between these two different of this standard and the references level. So here you can see this is the standard formula where we use to calculate the power level in terms of dB. Next is the dBm. We measure the power decibel in terms of milliwatt also. So that power ratio will be the very less. So here we use this power level for measuring the power signals. So this is the basic decibel power dB and dBm we used in the radio frequency. And in the next lecture series, we'll discuss about the RF model of transmitter and receiver sections. Thank you.